This is the story of our time. It is a story of challenge. It is a story of opportunity. Our world is moving faster than ever before. It compels each of us to redefine what it means to be successful in our life, in this time. We have come to understand that true success goes beyond human having to something more powerful. Human being. New Brunswick can lead the way. In this place, at this moment, we can tap into the greatest of all potentials. Our own. For each of us, there is tremendous opportunity. In all of us, unlimited possibility. Our way of life and the values we share will be our guide as we journey towards self-sufficiency. For here, in New Brunswick, you can be yourself. You can belong. You can be better. This is truly what it means to be in New Brunswick. This is our story. This is our time. This is New Brunswick.
Aside from our interest and commitment to the Edelman Prize and the OR community, we all have something in common. We have traveled on highways to come to this event. Let's not forget how significant a role highways play in the day-to-day activities of our families, our communities, and our businesses. Good afternoon. My name is Dale Wilson. I'm the Assistant Deputy Minister of Transportation in the province of New Brunswick. It's my job to help lead the rejuvenation of the agency from the inside out in a way that allows us to intelligently move forward in a period of constrained resources. Right now, New Brunswick is delivering a high-quality and sustainable highway network through the practical and effective implementation of operations research. Today, we're going to share our success story with you. The New Brunswick Department of Transportation is charged with the management, maintenance, and rehabilitation of roads and highways in the province of New Brunswick, Canada. Our mandate is to support the economic and social goals of the province by managing, maintaining, and providing a safe and effective transportation system. Compared to other jurisdictions in Canada and the United States, New Brunswick is largely rural and relatively small, both in population and in area. Population is just over 750,000. But at the same time, we are responsible for 18,000 kilometers of provincial highways and local roads, 2,900 bridges and a number of ferry crossings, tens of thousands of culverts of all sizes, and a host of other assets that comprise our civil infrastructure network. This amounts to the highest kilometer per capita transportation network in Canada and is supported by the taxpayers of the province. Across North America and globally, jurisdictions are struggling with the issue of aging infrastructure. We're all familiar with rough and cracked roads, potholes, and the severe consequences associated with bridge failures. The backlog of unmet construction and maintenance needs, known as infrastructure deficit, is a pressing issue. Preliminary estimates for the period 2006 to 2016 found that $97 billion is required Canada-wide for capital investment in transportation. Deferring maintenance or inadequately addressing repairs leads to much higher rates of deterioration and repair costs that can equal the cost of the original asset. Research has shown that spending $1 to keep a road in good condition prevents spending up to $7 to reconstruct it later on. Besides being dangerous, driving on rough roads accelerates vehicle depreciation, reduces fuel economy, and prematurely deteriorates tires and suspension. Typically, rough roads add $350 annually to vehicle operating costs. So taxpayers pay for poor roads twice, first through higher reconstruction costs and then through additional vehicle operating costs. A key challenge for the public service entities is the need for long-term, sustainable, and sufficient funding to meet development, rehabilitation, and maintenance requirements for civil infrastructure. In this regard, the New Brunswick Department of Transportation is the same as every other transportation agency throughout North America. Our challenge was to find a way to improve the overall quality of all of our civil infrastructure with a very limited budget. The political reality is that ribbon cutting is more popular than preventative maintenance, and health and education spending priorities dominate budgets. We had no way to quantify, nor to justify funding requirements. We needed to be able to establish a long-term plan for strategic infrastructure investment that was based on science, and we had no idea of how we were going to do it. That's where our team and operations research came in. They conceptualized an approach that did away with planning and budgeting in silos. They implemented a solution that included all asset classes and moved from a fix the worst first approach to one of least life cycle costs. They developed a tool that optimized investments and scheduled maintenance and repair across all asset classes. The result has seen significant benefits to our department, our province, and the taxpayers. Today you will hear about a province that needed to act, and to act fast. Our infrastructure was deteriorating quickly. We will tell you why operations research was the only way that we had that would address the challenge, and we will describe the operation research underpinnings that advance the theory and practice of transportation asset management. We will show you an analytically driven process for evaluating requirements and scheduling maintenance and rehabilitation activity, and a tool for choosing among multiple and conflicting priorities over the long term. We've already produced savings to a taxpayer of $210 million and can see $1.4 billion additional dollars over the long term. And this is coupled with a significant overall increase in road quality. Next, I would like to introduce you to my Minister of Transportation, the Honourable Denis Landry.
Bonjour, mon nom est Denis Landry, ministre des Transports du Nouveau-Brunswick. Au ministère des Transports, nous sommes fiers que le groupe Informs et le comité des prix Franz Edelman reconnaissent la valeur de la solution inédite que nous avons appliquée à un problème bien réel et très complexe. Comme le reste de l'Amérique du Nord, le Nouveau-Brunswick doit faire face à un vieillissement de l'infrastructure routière dans un contexte économique très difficile. Pour prendre des décisions éclairées, en vue du transport sûr et efficace des personnes et des marchandises dans la province, j'ai besoin de renseignements complets et exacts sur le besoin en matière de remise en état de notre infrastructure routière maintenant et dans l'avenir. Notre système de gestion des actifs, fondé sur la recherche opérationnelle, répond à ce besoin et me donne l'assurance que nous prenons les meilleures décisions pour favoriser la durabilité à long terme des biens publics et leur gestion adéquate. Je suis très fier de cette solution conçue au Nouveau-Brunswick.
Good afternoon. My name is Kim Matheson. I'm the Executive Director of Engineering Services for the Department of Transportation. Today I will outline the challenge we are facing, the requirements we set out for this project. Informed decision-making and effective resource allocation are significant and complex challenges when dealing with aging assets, insufficient funding, and large and diverse inventories, including highways, bridges, culverts, ferries. Add in competing budgets and other priorities, and asset life cycles that stretch over decades, and the problem seems almost insurmountable. And all of this within an organization that's driven by political masters and a 4-year election cycle. As a result, civil infrastructure agencies often find themselves resorting to management protocol, often known as fix the worst first. That is what we've been doing in New Brunswick and is typical across North America. By the year 2000, this approach has resulted in many of the New Brunswick roads that have deteriorated to a failed condition, requiring complete reconstruction at a very high cost. A 2007 plot of our pavement age distribution clearly illustrates this problem. As you can see, we had a significant portion of pavement older than 17 years. That's the maturity age for asphalt pavements. And in addition to that, another wave of pavement that existed was rapidly approaching that maturity and would require significant investment in the next 5 to 10 years. Looking forward, we're projecting an ever-worsening situation, since by the time one road kilometer was replaced through reconstruction, 2 or 3 additional kilometers were entering into the failed condition and would also need to be replaced. Within our department, we believe the existing level of infrastructure renewal funding was not enough to maintain our highway network in an acceptable condition. In fact, we believe the problem was infeasible, given our budget, the existing road condition, and short time frame we had available to address it. Roads were deteriorating faster than we could repair them. Our infrastructure was literally crumbling. But we didn't have a way to show this to government leaders. We needed a radically different approach, and we needed to act fast. We needed a solution that clearly demonstrated to decision makers the full scope of the issue we faced, gave a solid justification for a long-term budget increase, and allowed us to start immediately, and then over time adding more assets and data as they became available. Our solution had to be able to consider multiple assets in the same model and had to perform trade-off analysis and network-level planning that would allow optimization across all asset classes over the long term. It had to model asset use due to socioeconomic factors and fluctuating traffic conditions as well. It had to deal with adjacency and proximity issues. That is, the interrelationships between pavements, culverts, curbs, sidewalks, signs, and other features. The solution had to allow for multiple and conflicting constraints, including budgets. And as a public organization, accountable to the taxpayers of the province, the department had to ensure that the plans would be transparent and defensible, enabling buy-in from decision makers and support from the public. Finally, the new solution had to be implemented within existing resources and without additional staff. Our first step was to investigate the state of planning and best practices and new technology approaches worldwide. While we didn't find a solution that met our criteria in the transportation sector, we did identify an OR-based solution that matched our criteria and had been successfully implemented in the natural resources sector at hundreds of sites around the world. In fact, the technology had become the standard for the forestry industry, which is a major component of the New Brunswick economy. It was based on an innovative combination of linear programming and heuristics and allowed the user to use multiple assets in the same model. Also, it used a natural modeling language that meant that our in-house analysts would not require expertise in optimization and operations research to perform their day-to-day tasks. The REMSoft technology that was identified also used an iterative implementation-oriented approach which fit well into the way we wanted to implement our solution. It let us use the data we had at the time to get started and add higher quality data and assets as time and availability and budgets allowed. Right out of the gate, we weren't trying to achieve perfection. Just wanted to improve as much as possible on what we were doing at the time. And as work progressed, we would adopt a process of continual improvement. So to begin, we built a long-term strategic LP model to answer some key questions. What is the appropriate level of funding to meet the required level of service? How, when, and where should rehabilitation treatments be applied? And how will this funding affect the overall condition of the network? With that information in hand, we moved to tactical planning tools to allow us to group assets together based on adjacency and proximity. Finally, we adopted a process for our engineers to review and assess the model results in candidate projects and work together to make final choices. Next, Hugo Funekes, Chief Technology Officer at REMSoft, will describe the technical, theoretical underpinnings of the solution.
Due to the highly spatial nature of the problem, the number of assets we had to consider, and the long time horizons involved, developing a single model that incorporated all aspects of the problem across space and time would have been difficult, and solution using exact methods would have been cumbersome at best. However, hierarchical planning approaches are used in a wide variety of applications. In this instance, the Department have adopted an approach which is based on problem decomposition and uses separate but linked models to solve the problem in stages and at increasing levels of detail. In the first stage, an LP model addresses the long-term strategic aspects of the problem. This tackles many of the decisions necessary for the global planning problem, and the resulting schedule of activities forms an excellent starting point for the operational planning stages that incorporate increasing levels of spatial resolution across shorter planning horizons. In the second stage, we use the schedule from the LP along with a heuristic algorithm that uses adjacency and proximity relationships to create more spatially reasonable, spatially explicit schedule of activities. This algorithm takes a meta-heuristic approach, incorporating Monte Carlo integer programming for initial program grouping, bipartite matching and enumeration for initial scheduling, and a greedy algorithm to achieve balanced workflows and costs. And at the operational level, candidate projects are given to program managers, who then make final expert judgments on whether the model has suggested valid candidates. They review performance and look at videos of the highway surface and make adjustments for reasons such as functional improvements, operational considerations, and non-condition factors such as safety. And of course, directives and operational budgets are monitored to ensure the overall program development reflects the strategic treatment established by the global LP model. It's easy to see the difference between good and poor quality roads. However, to develop a mathematical programming model requires more rigorous and quantifiable methods. Fortunately, road quality is described through the use of numerical indices that have been developed according to international standards. For example, the International Roughness Index is a measure of road roughness. It is calculated by taking calibrated measurements with a laser while driving over a road. It's also fortunate that these changes in these indices are predictable over time and are available using one of several pavement management systems. A key point to notice on the chart is the nonlinear form of this curve. The deterioration rate stays steady for some time and then begins to accelerate quickly. End of useful life is another important concept in pavement management. Asset deterioration curves are specific to each various classes of roads, and depending on the road class and the nature of the last treatment, end of useful life can occur from 5 to 15 years after the last road repair. Another consideration is that as the asset deteriorates, the number of treatments available will change, and the costs associated with them can increase in magnitude dramatically. An early step in the development of the model is to determine the number of unique instances of these curves that are required, and then to assign them to the appropriate curve in each class segment of the 18,000-kilometer highway network. Once treatment alternatives are defined, deterioration curves for each road class are developed, and the current inventory of assets are initialized, the conceptual modeling framework for asset management is essentially complete. The LP notation you see for a particular scenario looks like what you see on the screen behind me. I know it's too small for you to read, but I've given the judges a handout and can make more available if necessary. The objective in this case was to minimize discounted costs, while the constraints were to reduce the total kilometers of poor highways. And by ignoring the adjacency and proximity relationships and constraints for the moment, results in an LP that can be quickly solved with commercial LP solvers. The resulting solution addresses the strategic questions of appropriate budget levels and rehabilitation activity, and provides a schedule of activities to meet the department's objectives of service levels. That is the required condition for the roads over the entire planning horizon. However, we aren't starting now with projects that are grouped and ready to implement. At some point, spatial relationships at the project level must be addressed. The reason they were ignored at the strategic level is due to the combinatorial nature. For example, if the department broadens the definition of proximity from two physically touching each other to considering all road segments within 20-kilometer radius, they increase the number of proximal relationships from 28,000 to over 2.8 million. And given the department considers radii as large as 50 kilometers for grouping, problems can become very, very large. However, from our experience in spatial planning, we know that problems of this nature can seem largely intractable to solution by exact methods. Therefore, we employ heuristic methods that quickly generate feasible solutions that are amenable to input from non-OR experts. Typically, the spatial schedulers run for 10 to 20 minutes, generating hundreds of solutions, and the top 5% are usually retained for consideration. Next, I would like to introduce you to John McNaughton, Manager of the Asset Management Program at the New Brunswick Department of Transportation. John will describe the solution and planning process as it is working today.
As program manager, I was tasked with finding the answers to the following questions. How, when, and where should treatments be applied? What will be the effect on overall condition of the network? And what is the least cost for maintaining the status quo condition of the network? I should point out, while that I use operations research every day, I don't have to deal with the math. I understand optimization and heuristics, and the natural modeling language used in the REMSOFT modeling framework lets me develop a sophisticated LP model to address these questions. This slide shows the components of one of my models. To build my model, I needed to be able to describe the asset base, define metrics for road quality over time, specify how treatments for improving roads work, and specify desired outcomes. Only the last part, desired outcomes, requires any knowledge of OR. I need to know how to specify my objective function and the constraints I want to employ, such as budget or changes in road quality over time. Let me show you what I mean. In this example, my objective was to minimize total expenditures over a 20-year planning horizon. I would enter it as you see it on the top right of the slide. By the same token, if I had a constraint limiting my annual budget to $140 million in the first year, and another to ensure the number of poor roads do not increase, I would enter those constraints as you see them here. And that's it. That's all I have to do to change my model. The ease at which I can set and change my model is very important to the department, since scenario and trade-off analysis is a key component of what we do. We regularly get requests from our minister and other central government departments about the impact of a change in plans or budget. For example, if the minister is getting heat in the legislature related to our highway system and asks us about changing the plan, I can easily change an objective or constraint and re-optimize. I can show them the real effect of deviating from the optimal plan, and I can calculate the actual costs related to it. Once I describe what was in my model I showed you earlier and specify my objectives and constraints, the software takes care of all the other housekeeping details for me. It reads my model, translates it into a matrix, and hands it off to a commercial solver, which solves the matrix and hands the results back to me. Outputs from the LP model include detailed schedules of actions to be performed to meet the objectives and constraints we specified, as well as the projected values for all key performance indicators. In the example I have here, we can see the cumulative cost over a 20-year planning horizon for bridge and highway rehabilitation, as well as annual expenditures based on an objective of minimizing total costs. Decision makers at the highest levels use these long-term strategic results to answer broad questions relating to funding levels, activities, the potential for new treatment options, and so forth. Once final decisions have been made about these issues, the problem then shifts to how to implement the strategic plan on the ground. A key issue here is that the candidate projects identified by the optimization need to be grouped into functional projects such as those Hugo described earlier. Just because the spatial constraints were not considered in the strategic model doesn't mean that we can't identify the location of their treatments and their associated timings. We can. All the attributes and outputs in the model are linked to our maps so we can explore the strategic solution spatially as well. This is an important tool for us in communicating our plans to politicians and other stakeholders. We can show them exactly where and when an activity will be happening over the long term. At the same time, many of the scheduled projects still need to be modified to meet operational realities, such as minimum contract size, potential disruptions to traffic flow and safety. We need to group projects together in a way that makes sense from a spatial standpoint to achieve this. Here's an example of a scheduling maintenance on a single asset type. While the optimized solution meets the objectives for the strategic level decision-making, it doesn't account for important subjective issues like neighborhood disruption, and it ignores potential for capturing project size and related benefits. On the left side of the slide, we can see the unmodified treatment schedule for a neighborhood subdivision. On the right, the adjusted schedule after processing with the spatial scheduler is shown. Notice how the projects are more naturally grouped and make more sense from a logistical standpoint. Once I have candidate projects identified and grouped together, I turn them over to the district regional planning teams for evaluation and input. They scrutinize the candidate projects for potential problems, considering issues ranging from contract letting to reviewing video of road surfaces to verify road condition. Changes to the candidate projects may require only minor adjustments, or they may ultimately lead to changes in the strategic model. And the hierarchical approach we have taken facilitates adaptive management and lets us build in a process of continuous improvement, something we set out to accomplish from the beginning. Next, Kim Matheson will describe to you the impact the solution has had on our organization and some of the benefits we are seeing as a result.
Our asset management solution has met all our criteria we set for ourselves at the onset of the project. The very first and most important benefit we realized as a result was that we could now clearly demonstrate the feasibility of the old approach, the infeasibility of the old approach, and the long-term benefit of the least life cycle cost approach, and the need for substantial funding increase. Let's look at what we found in a series of scenarios we ran early in the project. To illustrate the consequences of each scenario to senior management and government, we used a simple performance indicator of the total number of poor roads in the province. First, we decided to see what level of service we could attain with a traditional $50 million budget using operations research approach. As you can see, continuing this way would have meant that the number of kilometers of poor roads in poor condition would have continued to grow at a rate that was beyond the ability for us to control. Intuitively, our management knew the problem existed all along, but the magnitude was really quite a shock. In our second scenario, again using operations research approach, we doubled the budget. This made things much better. However, it didn't improve the overall situation. In other words, we gained nothing in terms of reducing the number of poor roads. That was surprising. It showed that the normal funding levels, which had been systematically reduced over the years, were so inadequate that even doubling the budget would not allow us to maintain even status quo. Next, we changed our objectives and constraints to find the least life cycle cost to achieve our goals. Our objective was to minimize the number of kilometers of poor roads, subject to a fixed budget and achieving our target service levels by a certain point in time. This told us that a threefold increase in funding would be required if we wanted to reach our objectives. As you might expect, we started to question the results. Well, who couldn't achieve better roads within triple the funding? We needed to find out what would happen if we significantly increased the budget, but we did things the old way. That was the key, using no optimization and the fix the worst first approach. We used a rules-based simulation to determine what would happen if the same threefold increase in funding was used, and take a look at what we found. This sealed the deal, as it were. The number of poor roads increased almost as quickly as our traditional $50 million budget, despite the tripled funding. Our analysis made it apparent that the selection of what assets to fix and when was just as critical as the funding level. Simply increasing funding levels with the old approach to planning would not improve the overall network condition. As a result of our $2 million development investment in the asset management system, savings are tracking our projections. We have saved $210 million to date, and we are projected to save $1.4 billion discounted over the next 20-year planning horizon, even taking into consideration the significant increase in funding we receive from government. The $1.4 billion savings are calculated by subtracting the projected cost of the optimal approach, $2.2 billion, from the projected cost to attain the same condition of the road network using the traditional fix the worst first approach, $3.6 billion. Once the solution was implemented in 2007, the department halted the growth of poor roads. It's important to note how closely our actual results since 2007 track our original projections. This is further evidence that our solution provides us with the information and the plans we need for our ministers to stand up in the legislature and justify the request for sustained funding for the program on an ongoing basis. This table shows us the percent change in the number of kilometers of highway rehabilitated since we implemented the asset management system. At the onset, we made a dramatic shift to maintenance on the road of the younger surfaces than the 20-year-old roads. In addition to an overall increase in close to 300%, you'll notice that the older surfaces are still being treated. The focus is directed more to the preventative maintenance, the less expensive treatments. Implementing our solution has transformed the way we perform the business of managing public infrastructure, resulting in improved overall management oversight, and has impacted our organization in a number of ways. The solution has removed the politics from paving. As a result of the mathematical optimization techniques and the clearly defined goals and objectives, strategies and plans are now more transparent and easily defensible. The new solution lets us make long-term decisions with more confidence and commitment. And because the consequences of deviating from the optimized plan can be easily quantified and communicated back to the stakeholders, politics has largely been removed from the decision-making process. Economic and environmental benefits arise out of an overall improved infrastructure and planning process. Earlier and more coordinated rehabilitation leads to less intrusive, energy-consuming highway treatments. In addition, the optimized life cycle management approach reduces the annual maintenance demand and associated costs. Smoother roads and more environmentally friendly approaches to reconstruction and lowered infrastructure debt are all positively impacted. The new approach has also broken down communication barriers and provides a touchstone to every manager in the department who are increasingly reliant on it for information and analysis. This approach created new levels of collaboration across the organization and helped to dismantle barriers across silos, allowing managers and executives to pose what-if questions and explore multiple scenarios quickly to ensure all relevant decision-making avenues have been explored. To date, the department has successfully demonstrated the benefits of operation research and implemented the solution within our corporate asset management system framework. Since the solution was implemented in 2007, bridges and culverts have been added to the model and will be included in the 2010 planning cycle. As a part of our continuous improvement approach, we will continue to add higher quality and more current data to the model to better optimize demands and life cycle characteristics associated with our large asset inventory. In addition, other assets, including ferries, buildings, signing, lighting, will be introduced into the model. Once this is accomplished, the model will then be used to provide direction with respect to modeling carbon targets, environmental permitting, and safety enhancements. We are also exploring collaboration beyond the Department of Transportation. Other departments in our province and other jurisdictions are learning from our experience and will continue to devote our expertise and passion to furthering the benefits of operations research in infrastructure preservation. Next, I would like to introduce you to our Honourable Sean Graham, the Premier of the province of New Brunswick. Following his remarks, Dale Wilson will conclude the presentation for us.
Transportation. It's not just about economic development. It's about our quality of life, our social development, and connecting people in regions. It's about connecting communities to opportunity. And New Brunswick's asset management system was designed to help the Department of Transportation rehabilitate our highways, and we remain very committed to it going forward. This system is transforming today the way the government makes strategic infrastructure investments. This system identifies the right treatment at the right time and the right place to make improvements to our infrastructure at the lowest cost to taxpayers. So in other words, we've taken the politics out of paving. Now the system applies operation research technology to illustrate how roads and bridges deteriorate over time. And today, we are seeing the benefits as our government is making our highways safer and more efficient while supporting our people and communities.
In a relatively short period of time, New Brunswick has realized $210 million in savings and will continue to realize significant savings on pavements alone. Over the coming years, as the system is expanded to include the remaining transportation-related infrastructure, this figure will increase significantly. Beyond improving the overall infrastructure quality, our solution will also lower annual maintenance demands, provide a higher level of service to the public, and benefit the environment through fewer energy-demanding and intrusive rehabilitation activities. Department leaders and team members now also have increased confidence and clear evidence that their decisions and plans are supported by facts and are delivering the desired results. In fact, it's not uncommon within the department to hear people ask, what does asset management say? Since its implementation in 2007, the solution has continued to prove its value beyond the significant savings to taxpayer. Through this work, New Brunswick Department of Transportation has become a global leader in the field of asset management, and our success has attracted the attention of transportation officials around the world. Proof of the change is evident by the support and focus government has given it. The asset management system has been one of the key points in the legislature, in the Premier's speeches. It has garnered comprehensive media coverage. Our success is also sparking interest from other organizations in Canada, the United States, and around the world. In many provinces, in several states, Australia, Costa Rica, Uganda, New Zealand, they've all expressed interest in our solution. In a largely rural province where the roads, highways, and bridges are the lifeblood of communities, the department can now fulfill its mandate of providing a quality, safe, and effective transportation system, thus keeping New Brunswick's economy and communities vibrant. This has been a very challenging but also very rewarding journey for us, and we are delighted to be able to have shared our story with you. It's an honor to have been selected as a finalist, an Edelman finalist, and I want to say thank you very much for your time. Thank you.